So this is lecture number 12, and today we are likely to be going to finish reading theory. I guess whatever the lecture will be of 2 hours, 3 hours, 4 hours, I don't know. Anyhow, I guess I might be finishing it today. So today we will discuss about the entire thing, what are remainings and brings, UFDs, and the concept of reducibility, irreducibility, then Eisenstein's criteria, Gauss lemma. Those things we will discuss today. And the first thing I will define, and up till now, last lecture we have defined what is an Euclidean domain, what is an principal ideal domain, and now today and some properties of EDs, PIDs. That properties we have already discussed, right? So now we are going to discuss about some what is called UFD, what is called unique factorization domains, right? So what are UFDs? See, this is the theories I am taking. All the theories, whatever I am writing and I am teaching, that all the theories I am taking from the book of Damit and Foote, right? Damit and Foote. Okay, this all the theories I am taking from this book, and you can follow this. Okay, on the theories theories and the examples I am also taking from this book, right? So what is called what is a unique factorization domain? This is called UFD, and shortly it is called UFD. So unique factorization domains. What are this? This is actually this is called UFDs. What are UFDs? So an integral domain. Let me say the definition first. An integral domain. So UFD. I don't know. This should be here. I don't know. Okay. Yeah. So UFDs. What are UFDs? UFD is an integral domain, and UFD is an integral domain. You know what is an integral domain, right? UFD is an integral domain R in which every non-zero element R is an R which is not a unit, which is not a unit, has the following two properties. Has the following two properties. What are the properties? The first property says it says that this R can be written as a finite product of irreducible. R can be written as product of the finite product of irreducibles PIs of R. Not necessarily distinct. That means your R that is your R. That what is your R is R can be written as a P1, P2 dot some Pk. Okay, and the second property says that the decomposition is unique up to associate. This is the decomposition. Decomposition is unique up to associates. What is the meaning of this? Up to associate means it is differed by a unit. So if that is if your R can be written as some q1 q2 some q k l, suppose l, then l should be equal to k, that means the indexing should be same, and pi is associate to qi or qj, I guess. Okay, I for some I, that means the pi equal to some unit time qi, where u is a unit. This is the meaning of associate. So this if an element satisfies these two if every element of this, what is says the definition set an UFD is an integral domain in which every non-zero element R, if every non-zero element R can be written as uniquely in terms of the product of irreducibles, then we say that this integral domain is an unique factorization domain, that the factorization is unique, right? Unique factorization domain. So first, whenever we always talk about definition, then we should have to talk about what are the examples, what are the integral domains which are UFD. So first example that immediately should comes in your mind, what is the first example? So first example is, let me choose the color. So examples, first example that should immediately comes to your mind is field. Every field is trivially an UFD. Field is trivially, should have to be clear for, just wait for a while. Field is, oh my god, yeah, every field is trivially UFD, because if you take any element of this field, so every element is an unit. So whatever element you take in the field, that the factorization should be unique. Okay, every field is trivially UFD. So the second example that should in your comes in your mind is Z. Is UFD, because you take any prime P, you can factorize some P1 to the power alpha 1, Pk to the power alpha k, right? But your all the whatever you take, this should be unique, right? Whatever if you have take any other some q1, that they will be same, because they cannot be differed by a unit. What are the units? That is, units are plus and minus 1, plus 1 and minus 1. So they can be differed by a unit, nothing more than that, right? So Z is an UFD. So the third example is non-example. So Z2i. What is Z2i? Z2i means A plus 2bi, where A and B are coming from integer. So is it a UFD? Is it a UFD? So take an element 4. 4 is a member of Z2i, right? And 4 can be written as 2 into 2, and also can be written as 2i into 2i, is not it? But this has two representation, right? This 4 can be written as 2 into 2, and also can be written as 2i into 2i, right? But is it 2 equal to some unit time 2i? Is it true? See, if this is UFD, then this element has to have the differ by a unit, right? But this is not a unit. 2 cannot be written as a 2. See, What are the units in this Z2i? First of all, that you have to be clear about one thing. What are the units? Units in Z2i. What are the units in Z2i? So unit, those elements are units whose norm is plus or minus 1, whose norms are plus or minus 1. So norm of a plus bi, if a plus bi is a unit, a plus bi is a unit, 2bi, sorry, a plus 2bi is a unit in Z2i, then norm of a plus 2ib should be equal to plus minus 1, either plus 1 or minus 1. So what are the norm of a plus 2ib means a square plus 2b square, a square plus 2b square equal to 1 or minus 1, right? That means a has to be equal to plus minus 1 and b has to be equal to 0. There is no other choice. This implies that a has to be equal to plus minus 1 and b has to be equal to 0. There is no other choice, right? So what are the units? So units are a plus b is a unit. The value of a is plus minus 1 and b the value of b is 0. So that means the units are plus minus 1. But can you write this 2 as a plus 1 or minus 1 times 2i? Is it possible? It can never be written as in this format. So this Z2i is not a UFD. This is a non-example, right? So this is not a UFD, okay? Because 2 and 2i, this 2 and 2i are not associate. Associate means they cannot, they is differ by unit. That means if you multiply as a unit here, either here or there, you should have to get your second one. That means one can be written as a unit times the other, but you are not able to do here, so right? So 2 can never be written as a 2i times something unit. So this element is 4 can never be 4 is not 4 cannot be written as the product of irreducible up to associate. So that means this Z2i is not a unique factorization domain, UFD, right? So examples and non-examples are done. So what else I can talk about? So let me say proposition. Okay, just a second. What is happening? Okay, black color is not available. Okay, so proposition, what it says, in a UFD every prime element is irreducible and every irreducible element is prime. In a UFD prime element if and only irreducible element. Okay, so proof is completely easy proof, very easy. So which case is easier? This case is we have already done. In any not only in any integral domain, this is true. In the last lecture we have also proved it, right? In any integral domain every prime element is irreducible, but in a UFD the special thing which happens is every irreducible is prime. So this we are going to prove here. So this, suppose PB and irreducible, like PB, this is so let P, this is P, right? PB a non-zero, P is non-zero irreducible element. P be a non-zero irreducible element. We have to show that this P is a prime element. In R, okay, and R is given to be UFD, right? So now we have to show that P is prime element. P is a prime element. How do we show? So let prime element means if P divides AB for any AB inside this ring R, then you have to show either P divides A or P divides B. That you have to show, right? So let P divides AB, where A comma B inside this ring R. This means that AB equal to some PK for some K, right? So since you are in a UFD, then the decomposition is unique up to associate. No, since you are in a UFD, then whatever the decomposition you have written for AB equal to PK, that should be unique up to associate, right? Since you are in a UFD. So the decomposition is unique up to associate, right? So since you are in a PID, then your decomposition is unique up to associate, right? Is not it? So you have two cases. If one of them is unique, then yeah, associate, right? So if one of A or B are unique, then one of A or B are unique, then B equal to A inverse PK. This implies that P divides B, or A equal to PK B inverse. This implies that P divides A, right? If this case, and if not, this implies P is prime. If not, P equal to some unit time A, or unit time P equal to some unit time B, right? This implies that you can unit inverse, you can take it unit inverse, you can unit inverse into P. This is equal to A, or unit inverse into P, inverse into P. This is equal to B. This implies that P divides A or P divides B. This implies that P is a prime. In the P is a prime. In both the cases, the P is going to be prime. So P is a prime element. Prime element. Just a second. What is happening? Okay, so I cannot say anything. Okay, so the next thing, what I am going to, is it understood? So I think it should be understood. What is I have written here? So you just see here, in a UFD, that every prime element is irreducible, and the converse is also to if irreducible is, and that in any integral domain, every prime element is irreducible. That we have already proved in the last class, right? So you need not be worried about that. So we have already proved that. So now suppose you are assuming one prime element P, and you want to show that irreducible element P. Now you want to show P is a prime. So what is the best possible thing? What you should do? to show that P is a prime element. So P is a prime element means if P divides AB, then as by definition of prime element, so P divides AB, then either P divides A or P divides B, right? So this is the definition of prime element. So now suppose P is a prime element. Now, so suppose P divides AB. No, sorry, P is a prime element you have to show, and you have assumed that P divides AB. That means this AB can be written as AB is P times K. It's not it. If something divides, then there should be some factor, na? So AB equal to some P times K. But you are in a UFD. That means the factorization, what about the factorization for AB? This is unique up to here, right? So if one of A or B is unique, then you can see AB is also equal to PK. That means one of them has to be a unit, because you are in a UFD and the factorization is unique. So if one of A and B are unit, then B can be written as A is unit, then A inverse, you can talk about the inverse of A. That's why I have written as A inverse of PK. That means P divides B. It's not it. It essentially means that P divides B, right? So suppose A is a unit, sorry, B is a unit, then you can talk about B inverse. So you can take PK B inverse AB. For the decomposition of AB can be written as A equal to PK B inverse. That means P divides A. That means either P divides A B. That means P divides A B, or P divides A. That means B is a prime. Suppose if not A and B are not unit, that means the P equal to some unit time A, or P equal to some unit time B. Now you are just adding this unit inverse, so that is essentially means that P is a prime element, right? So that much I guess it is fine. So now okay, now one proposition is also here. So another proposition, I'm not going to prove this, you can easily find it in the book of Dummy and Food. Every PID is a UFD, but not conversely. Every PID is a UFD, but not conversely. So you can find it in the Dummy Food book. I can give you the proof. Where is it? Yeah, this I have proved. Okay, so I guess every principal domain is a unique factorization domain. This is a theorem, right? So this is the proof of this theorem. A little bit lengthy, but you should you have to this is the theorem. Every principal ideal domain is a unique factorization domain. Okay, so this is the proof. This is a little bit lengthy. I'm not doing this here. Okay, this is theorem. You can take it as a theorem. Okay, so now you know what is a UFD, what is a PID, what is a ED, what is a integral domain. So can you differ both of them? If somebody asks you give an example of give an example of this which is not this, which is this not this. So can you? So I can give you. So every field. So you know that this any field. So proof is proof. The proof. Here the proof is Dummy Foot. Refer. So now what can you do? Every field. So you know that every field is a very nice structure. So every field is contained in Euclidean domain. That means every Euclidean domain is a field. Every field is an Euclidean domain, but the converse is not true. For that I will give you example. And every Euclidean domain is a principal ideal domain, you know, right? And every principal ideal domain, but not equal, right? They are not equal. Every principal ideal domain is a unique factorization domain, right? See here the last theorem. Every PID is a UFD. Okay, and UFD is contained, everything is contained in ED because integral domain. So what? So can you give an example of the integral domain which is not UFD? For this example is Z2I. We have I have just explained it, right? So can you give an example of a UFD which is not PID. This is ZX. ZX is an example. So can you give me an PID which is not ED? Of course. But you have to work something. This is actually Z of 1 plus something square root of D square root of D by 2. Whatever you take, D is a square free integer, or minus D you can take, minus D. D is a square free integer. So can you give an Euclidean domain which is not a field? You can take it this Rx, ZX, sorry, Rx means the real number, ZX. Okay, so these are some difference, right? And one more thing I want to say, that if F is a field, this means that F is an Euclidean domain. This means that this F polynomial ring over X is an Euclidean domain. This implies that, this means that this, if it is easy, then this Fx is a PID. If this is a PID, this means that this Fx is a UFD. If it is a UFD, this implies that F is a UFD. I have not proved this theorem, but Fx is UFD if and only if F is UFD. Have I proved it? No, I have not proved it yet, I guess. Okay, so that much is for UFD. Now I am to say about discuss about some polynomial rings, and you know what is a polynomial ring and what are the structures of them. So polynomial ring, you know what is polynomial ring. So oh my god, what is happening? No problem. Okay, so let R be a commutative. Let's talk about some commutative ring, right? Let R be a commutative ring. Let R be a commutative ring. Let R be a commutative ring with unity, CRU. So you can talk about the ring. This is a polynomial ring over this is some all those polynomials Px, so that the coefficient of Px are in the ring R. This is a polynomial ring, you know, and you also know one thing, that is R is an integral domain. This implies that Rx is an integral domain. This is very easy to check, is an integral domain, right? So now, and the other thing what you know, that R is an integral domain, the units of R and the Rx are same. If R is an integral domain, if R is an integral domain, then the units of R and Rx are same, right? So can you show this? How do you show the units of R and Rx are same? So let me give a brief idea of this proof. So let Px be unit in Rx. See, one thing is clear, right? If it is unit in Rx, then it has to be unit in, sorry, if it is unit in R, then you have to be unit in Rx, because, and now I am taking that Px, let Px be a unit in Rx. That means there exists a Qx in Rx such that Px Qx equal to 1. You compare the degree. What are the degree? Degree of Px Qx equal to degree of Px. So degree of this equal to degree of 1. This implies that degree of Px plus Qx equal to the degree of this element is degree of, in integral domain you know that degree gets added, degree of Qx equal to degree of 1 is 0. This forcefully tells you that the degree of Px equal to degree of Qx. That means Pu and Q are constant polynomials. This essentially means the degree of Px equal to degree of Qx, because the degree can never be negative, right? So degree of Px has to be equal to degree of Qx. That means that P and Q are has to be equals to 0. This implies that the P and Q are constant polynomial. That means that Px is a unit in Rx. Px is a unit in Rx, right? Sorry, unit in R. I have taken to be and the converse. What about the converse? Converse is, I guess, converse is trivial. So I don't think the converse is very, and this is an idea, right? So now I am going to, so what else I should have to, okay, so I should have to tell about now polynomial rings over more than one variable. Should I have to do, and before that what should I do? Okay, let me do one thing. Suppose you have a polynomial, and if you have a ring homomorphism from this polynomial ring to this polynomial ring, now in a polynomial ring, if you have polynomial map, then you can, if you have the image of x and 1, you can generate everything. So this is an easy task. I am not going to do this. So now I am going polynomial ring over more than one variable. Polynomial ring over more than polynomial ring in many variables, in 2 or 3, generally 3 variables. So this is an important, okay, for exam perspective this is important. So suppose R is a ring, let R be a ring, and xy with 2 variable, define R x y, set up all polynomials in x and y, set of all polys in x and y, coefficient from R. It also can be written as, this can be written as Rx is a ring another and variable y. set of all polynomials in y whose coefficient, this is actually set of all polynomials in y whose coefficients are from Rx. Is that it? Similarly, you can define for n variable. If you have R of x1, x2, xn, you can think of as x1, x2 up to here xn minus 1 over xn. Okay, so this is the definition of polynomial ring. Now let me come to some questions, otherwise without question it's very difficult to understand. Not very difficult, it's a little bit hard to understand. So now suppose you have an ideal, you have a ring, let you have a ring, so let your ring is given to be q x y, the polynomial ring in two variable x and y, and the coefficients are from rational numbers q, and you have an ideal, this is ring, this is ideal I is ideal generated by x, ideal generated by x. Now what is ideal generated by x? Suppose what is ideal generated by x, which is actually nothing but all those, the multiples of all those polynomial pxy into x, where pxy are in qx, right? So this is the definition of the ideal generated by x. This is a very simple definition of ideal generated by x. So what you know, in one variable we know that if you have f from Rx to R, the evaluation map, what is the evaluation map? Any px you take, it goes to p of 0, right? And here the kernel is ideal generated by x. So now from here you can use the first isomorphism theorem, that the Rx by ideal generated by x is isomorphic to this R. This is a one to ring homomorphism. So this, the first isomorphism tells us that this is isomorphic to this R, right? The first isomorphism theorem tells us that this is isomorphic to R. So now what can you think about this, the two variable case? Same, right? The two variable case is also same. Your ideal generated by x, now the same thing you can, define. See, your qxy, what your qxy is, your ring is qxy, it can be written as q, also can be written as qyx, it also can be written qyx. This is qy is a ring and x is another variable. So now you can think about this qy over x by ideal generated by x is isomorphic to qy. Okay, so this is an integral domain but not a field, right? So this implies that ideal generated by x is prime but not maximal, maximal in qxy, right? So these small things are important. Sometimes these are important. So sometimes it's better to work with one variable. So that's why These small things are important. So now, so this ideal generated by X is not a prime, is a prime ideal but non-maximal, because this your Qy. What is the Qy? See, you know that R mod I is an integral is a field, is an integral domain if and only if this I is a prime ideal, right? And maximal if and only if this is a field. This is a field if it is maximal. So this you know. So in a PID you know that every prime ideal is maximal. Every non-zero prime ideal is maximal. So from here in a PID we know that in a PID every non-zero prime ideal is maximal, but your X in QXY is prime but not maximal. This implies that this QXY is not PID, right? Because if it is PID, then every prime ideal has to be equals to maximal, right? But this ideal is prime but not maximal from here. Okay, so that's the thing actually. And how it comes to be this isomorphism, let me show you how it comes. Is F, what was QXY to QY, you just define any Px comma y is equals to P of 0 comma y. So is onto, this is clearly onto. And what about the kernel of F? Kernel of F, all those Pxy such that P of 0 comma y is 0. This means that this is P of 0 comma y is 0. This essentially means that this is P of x comma y times x, such that P of x comma y is in Q of x comma y. This means that this is nothing but ideal generated by X. Okay, so the next question I want to talk about, that the ideal generated by I is ideal generated by X and Y, and your ring is QXY. Is it maximal or prime? Which one is true? So you can think about it. So you want to make and kernel to be ideal generated by X and Y. Then what kind of map you should take? For which your what kind of map F from QXY to Q or somewhere, such that the kernel of F is ideal generated by X and Y. What is this? This is actually x times P plus Y times Q, where P and Q are polynomial in QXY. So you want to map, right? So that your this is maximal plus prime something. Okay, so what kind of map you can take about? So you take map the P of any x comma y is goes to P of 0 0. So this map is an onto ring homomorphism, and the kernel is nothing but this. You can definitely verify the kernel is this, right? Kernel is this. So your Q of x comma y ideal generated by x comma y is isomorphic to this Q by first isomorphism theorem. So this implies that ideal generated by x comma y, and this is a field, is maximal and prime, right? Okay, so these small things are sometimes important, and now I am going to write an important question. What is that? And what is this question? Question is actually tells about your, yeah, okay, what is the question? So I'm writing two statement. Okay, so you just have to verify which one is true. There exists an injective ring homomorphism. There exists an injective ring homomorphism. Injective ring homomorphism from QXY by ideal generated by x square minus y square to QXY by ideal generated by x minus y square. And statement 1, statement 2. Okay, if f be any field, then if f be any field, then your fxy by ideal generated by x square minus y square is isomorphic to fxy by ideal generated by x minus y square. Which one is true? Can you so this is the question actually, right? Let me change the color. Yeah, okay, so is this true or which one is true? I am leaving it to you, and this is very important question. Okay, so this is a true false. Which one is true? True or false? True or false? Okay, think about it. You can pause the video. You can think, right? I'm giving you 1 minute. Now it's 4:16. Okay, I'm giving you 1 or 2 minutes to think. Let me do one thing. Okay, have a think. So now I'm going to which one is true? What do you think? So can you see one little clue here, that is it an integral? Is that has any this field? What is if be any field, and you have this? Is this has any zero divisor? Can you see this has zero divisor? This is very clear, because you can take x. See, first I will come to this. First I will come to this. So okay, so first come to the clearly. You can see clearly this fxy by ideal generated by x square minus y square has a 0 divisor. But this has a 0 divisor. What is the 0 divisor? You can think at x minus y plus ideal generated by x square, two element x square minus y square into x plus y by plus ideal generated by x square minus y square. What is that? This is actually x plus y, x minus y plus ideal generated by x square minus y square. This is actually equals to x square minus y square plus x square minus y square. This is actually equals to 0. The 0 means x square minus y square, ideal generated by x square minus y square. So this means that this is a 0 divisor in here. So it has a 0 divisor, right? So this has a 0 divisor. So this field has a 0 divisor. What about this? What about fxy by ideal generated by x minus y square? What about this? So if you can do this, then the previous question will be solved. Previous statement will be solved, whether this is true statement or false statement, right? So what about this? What do you think about this? So you want to define a function f from fxy to somewhere to fx. I'm sorry, this fx in x variable fx such that your kernel is ideal generated by x minus y square. So what is the best possible thing you can talk about? So you just throw it if any px comma y, I guess. If at any px comma y, any polynomial px comma y is goes to p of x square comma x. So what can you think about this kernel? Such that the kernel is x minus y square. We have to make this kernel to be ideal generated by x minus y square. So what is this kernel of this map? So what is the kernel of this map? What is the kernel of this map? Can you say? All those polynomial px comma y such that p of x square comma x is 0. So clearly you can see that x minus y square. So can you see that x minus y square c, if your pxy is x minus x square, x minus y square, sorry, your pxy is x minus x square, this implies that p of x square comma x will be x. In case of x, you have to put x square minus x square. This is 0. This means that this x minus y square is a member of kernel of f. This implies the ideal generated by x minus y square is also a subset of kernel of f. Is that it? Yeah. So if this is so, so one thing is clear. So kernel of ideal generated by x minus y square is contained in the kernel f. What can you converse? What about reverse? So let p be an element in the kernel of f. This implies that p of x square comma x square comma x, this is 0. It's not it. So this you can think of p of x square comma x. What is p of x square comma x? So you can think of it as a I guess P of x square comma x, right? P of x square comma x is 0, and P is a member of this kernel F, right? X square comma x is equal to 0, but kernel F, okay. So can you write it in this format that x minus y square times q is 0. So how can we write this? P x square comma y square, P x square comma y square. How can I write this? X minus y square times q. I want this P to be the member of this kernel F, but can you write in this format? Because if your P of x square comma and P is a member of this kernel F, okay. P of x square x minus y square times q, where q, what is your q? Q is another polynomial, right? Q is another polynomial. Yeah, q is another polynomial. You can write. Yeah, I think you can always write, because q is another polynomial. So what whenever you will have this P of x square comma x is 0, this implies this, this implies this is true. But how do you see this implies this? P of x square comma x. And show this P is a member of this kernel F. Okay. No. I think you can write it in this P of x square minus y into q is 0, but somehow, so this will follow that this P is a member of, this will follow that this follow that P is a member of this ideal joint, because P can be written as, okay, this, there is a division algorithm. No, there is no division algorithm. This P can be written as x minus y square times q. This will satisfy that this particular types of polynomial satisfies. But what is the guarantee that this is exactly these types of polynomials are there? So this implies that this P is a member of, P is a member of ideal generated by x minus y square. So this implies that this kernel of f is exactly equal to ideal generated by x minus y square, right? So is this map onto, is f onto is f onto, let px be a polynomial in fx. Let px be a polynomial in fx. In the codomain, fx is a codomain, right? I need a qxy in fxy such that f of this qxy equal to p. So f of qxy, that means that q of x square comma x S is px, right? So choose q of x comma y is equal to p of y. So if we choose this, then your f of q of x comma y, this is actually equal to q of x square comma x, which is actually p of x. So this means that onto, this map is on onto. So also this is a ring homomorphism. So we have finally that f of x comma y by ideal generated by x square minus y, x minus y square is isomorphic to this fx. This is an integral domain. This means no zero divisor. So this means that this is a prime ideal. So this is a prime. So this is a prime ideal. So integral domain, it should not have any zero divisor. So it has no zero divisor. So the integral domain. So this has no zero divisor because this is isomorphic to this has no zero divisor. This means that f of x comma y by ideal x minus y square has no zero divisor, but f of x comma y by ideal generated by x square minus y square has a zero divisor. Just we have proved has a zero divisor. See, this has a zero divisor. What is this? So they can never be isomorphic. So this fx comma y by ideal generated by x square minus y square can never be isomorphic to this fxy by ideal generated by x minus y square, right? So this is they can never be isomorphic. So this is a false statement. False. So is this true? Is this true? So this is also a false statement, because see, they have asked here that q, whatever the field is, q x comma y by ideal generated by x minus y square, x square minus y square, there is injection. This is embedded in q of x comma y. That means there is injecting ring homomorphism from here to x minus y square. But how can it? This has a zero divisor. This has zero divisor. But this it has no zero divisor. But how it can be embedded in here? It has no zero divisor, but it has a zero divisor. But how it can be embedded here? So it is not true. False. Right? So also there is an alternative way to see this. Suppose there is an injection. That means the kernel is 0. So if the kernel is 0, then QX are ideal generated by the image. Okay, the image of this, but image of this is a subset of this. So this is also a same kind of thing is here. So this is also not correct. Means there can never exist an injection from qx comma y by ideal generated by x square minus y square into qxy by ideal generated by x minus y square. So I am giving you one question and to think. So what is the question? Which of the following are PIDs? Which of the following are PID? So the first is ZX by ideal x square plus 1. 1 is the 1. Okay, let me. What is B? ZX. C, CXY, and D, Rxy, R means the real number, xy by ideal divided by x square plus 1 comma y. Which of the PID? Think. This is the exercise question and this is a very easy question. Okay, so pause it and try to solve it. This is I am giving you the solution. What is the solution? So if it's you know that fx is a PID if and only if it is a field. So this is let me change the color. This is false because zx is a PID if and only if z is field, but z is not a field, so this is not true, right? And similarly cxy, similarly for cxy is a PID, cxy is a PID if and only cx y is a field. Sorry, cx is a field but cx is not a field. Similarly for y is not a field, is a field, but this is not true, so this is also incorrect. So these two are incorrect. So what else? What about this and this? So okay, first one, for the first one you can think of, you have a map, suppose f zx to suppose zi. You want a map, right? Somewhere initially it's not sure you have to map in the zi, but you have to make the kernel of f to be ideal generated by x square plus 1. But what is the best possible choice is you can think zi, and p of x goes to p of I. So what is the kernel of f? For which kernel of f will be x square plus 1, verify it, and by the first isomorphism theorem, zx by ideal generated by x square plus 1 is isomorphic to z of I, and the question says that this is a PID, but zi is a PID, right? Because zi is a ED, this implies this is a PID, so this implies this option is correct. What about the last one, D? Is it a PID? So similarly you can think of it. So you have to make a map from f from Rxy, R means the real number xy, to somewhere such that the kernel of f you have to make is to be ideal generated by x square plus 1 comma y. So you just take it to C, and you p of x comma y and x comma y goes to p of I comma 0. So you can verify this is the kernel of this map, and by the first isomorphism theorem, Rxy by ideal generated by x square plus 1 comma y is isomorphic to C. This is a field, this implies PID. C is a PID, so this implies that this option is also correct. So this and this option are correct, right? So another question I am giving you, you try to solve it. It's likely to be question solving session. So what is the question? The question is, okay, true or false? What are true or false options are actually zx z of x comma y by ideal generated by y plus 1 is a UFD. Question 2. What I can say, if R is a PID, if R is a PID and P is a non-zero prime ideal, P is a non-zero prime ideal, non-zero prime ideal, then R mod P has infinitely many prime ideals. Prime ideals. Finitely many prime ideals. And the third is which one of them are true and which one of them are false. You have to say, if R is a PID, R is a PID, then every subring containing 1 is again a PID. This implies every subring containing 1 is again a PID. Just verify which one of them are true, which one of them are false. I am giving you 1 or 2 minutes to think. True or false? Let me check. What has happened to her? Okay. Which one of them are true and which one of them are false? What do you think of the first one? Zxy by ideal generated by y plus 1 is a unique factorization domain. What do you think of it? So similarly, you can you try to think of with a map, right? The for which the kernel is the ideal generated by y plus 1, and you can make onto ring homomorphism so that you can make this as isomorphic with to a simple structure, which is a UFD or PID or ED, whatever. So first one is an easy exercise, I guess. You try to make. So you make a map from ZXY to ZX. Okay, and you try to map this kernel of f. What if this map is f, then kernel of f is, try to make it as y plus 1, right? If it is y plus 1, and what is the map? Map is actually px comma y, p of x comma minus 1, right? So the first isomorphism z of x comma y by ideal generated by y plus 1 is isomorphic to zx, but zx is a UFD because z is a UFD. So this implies that this is a UFD. So this is a true statement, true. What about the second one? Second one says R is a PID and P is a non-zero prime ideal. Then R mod P has finitely many prime ideals. Is it true? R is a PID. You use the fact that R is a PID. This is R. R means not any arbitrary ring R. This is not a real number. So R is a PID and P is a non-zero prime ideal. In a PID, every non-zero prime ideal is a maximal ideal, right? So R is a PID and P is a non-zero prime ideal. That means P is maximal. If P is maximal, then R mod P is a field. So this has exactly two ideal. So this statement is also a true statement, right? This statement is also a true statement. Have you understood whatever I have told? R is a PID, that means P is given to a prime, that means the P is maximal. Because you are in a PID, every maximal ideal is prime, so this is maximal. If it is maximal, then R mod P is a field, and every field has exactly two ideal. One is 0 and one is itself. There is no proper ideal in a field. What about the third one? R is a PID. R is a PID, and every subring contains 1 is again a PID. This is exactly false. Is not it false? This is definitely it is false, because every subring, that means you can think of as ZX is a subring of CX, and this contains 1, but ZX is not a PID, so this is a false statement. So this much I guess you are comfortable with some questions of UFD and PIDs, right? Now I can think about some more. Have you interested in more questions, or should I have to move from another topic? Because I will finish this topic today. Whatever the ring theory is remaining, whatever, I guess 1 or 2 more hour, it will be more than sufficient for me to finish, to complete it. Okay, so okay, so I think I should have to discuss some more questions. So another question. So what is the question? So suppose you have the ideal, you have a ring CXY, and the ideal is generated by X plus Y. Ideal generated by X plus Y, right? You have this ideal generated by X plus Y. So what about think of the prime or maximal? What about think of the maximality and the primality of this ideal? So these kind of things are very easy, I guess. So this, you just map CXY to CX in one variable. You just either you can it CX or CY, but it doesn't matter. So any x, P of x comma y goes to P of x comma minus x. So this implies that this C of the kernel will be of x plus y. Kernel will be x plus y, ideal generated by, and C of x comma y by ideal generated by x plus y is isomorphic to C of x. C of x is an integral domain, but not field. So this is a prime, but not maximal. Okay, and this is an easy question, easier one. So question number 2 I can think of, and 2 more question I will give, 2 and 3. So you just check the primality of this ideal in CXY, and you have an ideal I is actually ideal generated by x comma y square minus 1, and ideal generated by xy minus 1. What do you think of them? You just check. I am leaving it to you as an exercise. Now I am going to study some new and finishing topic, what is called irreducibility of polynomials. Till now we have discussed about some reducibility, irreducibility of of elements, but now we will have to precisely we will work on the reducibility and irreducibility of polynomials. When do you say polynomial is reducible, irreducible? So reducibility, irreducibility. So this is a new topic, and namely it's called irreducibility and irreducibility of reducibility and irreducibility. Reducible, irreducible polynomials. Okay, so reducible and irreducibility of this polynomial. A polynomial, so let me define with start with the definition. A polynomial fx inside the ring Rx, big X, Rx of degree greater than equal to 1 is called irreducible. It's called irreducible polynomial. It's called irreducible polynomial over the ring R. Here R is a ring. This is understood. If it cannot be written as a product of two non-constant polynomials, polynomial of smaller degree. Otherwise it is called reducible. Otherwise it is called reducible. Otherwise it is called reducible. Yeah. So have you understood the definition? A polynomial if fx inside Rx is of degree at least 1 is called irreducible. That means if it can never be written as a product of two non-constant polynomial. It's a simple definition. So I think everybody should understand what is the meaning of this, right? So now example, what do you think about the examples? And every linear polynomial is by definition irreducible. Every linear polynomial is irreducible by definition, right? So now another example, example 1, example 2. Example 2 we can talk about, suppose fx equal to x square plus 1 over, it is irreducible over R, over R means real number. It is reducible over C because it can be written as x minus I, x plus I. This is a polynomial in Cx, this is a polynomial in Cx. So this is reducible over Z2 because this Z2 can be, this x square plus 1 can be written as x minus 1 whole square over Z2, because Z2 plus 1 and minus 1 are actually same. This is also going to be x plus 1 square. This is actually x plus 1 x plus 1 x plus 1. So this is irreducible. So, okay, so same polynomial can be irreducible over a field, can be reducible over a field. So it doesn't matter is polynomial reducible or irreducible. It totally depends on the underlying field, right? So totally depend on the underlying field, right? So okay, the example is over. So every polynomial, can you think of every polynomial of degree greater than 3 is always reducible over R? Is it every polynomial? Okay, let's keep this aside and we'll talk about that. Okay, so every irreducible element implies that irreducible polynomial, or irreducible polynomial implies irreducible element. So we'll come to that. So if F is a field and Px is irreducible polynomial over F, Acha, okay, I'll come to that. Let me choose some other color. In a field, every irreducible element means irreducible polynomials. In a field, irreducible element and irreducible polynomial are same. In a field, irreducible element and irreducible polynomial are same. Why? Because why this is? Let F be a field. Let F be a field and Px be an irreducible polynomial over F. Then Px can be written as some Qx times Rx, where Px is irreducible. This means that Qx or Rx is constant. If Qx is a constant, this means this is unit. If Rs is a constant, this is a unit. This implies that Px is irreducible element. Okay, I have to start with Px is irreducible polynomial. I am getting Px is irreducible element. Okay. You know what is a field of fraction? I have not defined it, right? So let's keep this. Field of fraction is the smallest field containing this. The smallest field containing. Okay, let's just define what is field of fraction. Field of fraction of an integral domain. Field of fraction. What is field of fraction? Field of fraction of an integral domain R of an integral domain R is the smallest field containing R. For example, field of fraction FF means field of fraction of Z is equal to Q. So this is field of fraction. So now I'm ready to define what is Gauss lemma. Gauss lemma, right? Proposition, one proposition is a very important proposition. It's called Gauss lemma. GAUSS, Gauss lemma. What is Gauss lemma? Let R be a UFD. It says about the UFD. It also you have to assume that R is a UFD. Let R is a UFD. R is a UFD with field of fraction if and let Px inside Rx be a polynomial. If Px is reducible in Fx, okay, the field of fraction F, okay, if Px is reducible in Fx, if Px is reducible in Fx, the field of fraction F is a field of fraction, then Px is reducible in Rx, then Px is reducible over Rx. That means if it is reducible in the field of fraction, then it has to be reducible in the ring. Okay. The more precisely, if you want to say, the more precisely, okay, let me change the color. More precisely, if you want to say the if is Px is time Ax time Bx, Ax and Bx are two polynomial, Ax time Bx for some non-constant polynomial, for some non-constant Ax and Bx, sorry, Ax and Bx are non-constant, for some non-constant polynomial in the field of fraction, non-constant, okay, Ax and Bx for some non-constant, then there are non-zero elements R S such that then there are non-zero R and S inside the field of fraction such that this R into Ax is equal to R into Ax equal to Ax. So I will define what is Ax, and S into Bx is equals to Bx. Both lie in Rx. Rx and Px equal to Ax times Bx. This X are actually, yeah. It essentially is that if you have Px in Ax times Bx, and Ax and Bx are two polynomial in the field of fraction, then there are non-zero R and S inside this field of fraction such that R into Ax equal to Ax and B into S into Bx equal to Bx, and both lie in Rx, and Px can be written as Ax times Bx. This is the actual Gauss lemma. So so let me start with some example. What are the example? So without example you will not be maybe understand, maybe it is better to understand. If your Px is equal Px is inside zx, right, and the field of fraction of z is q, you know, right, and Px is reducible over q. This implies that Px is reducible over z. This is the actual Gauss lemma. Okay, this is the actual Gauss lemma. This has a corollary. This is a corollary. For this is a corollary. What is says the corollary? Let me see what is the corollary. Okay, let me corollary. One corollary is here. One corollary says that let R be a UFD let R be a UFD and F be the field of fraction. F be field of fraction of R. F of R means the field of fraction of R, and Px is in and the Px is in Rx. The polynomial. Suppose GCD of the coefficient of that content, actually content of P or something, right? Suppose the GCD of the coefficient of Px is 1, that the content of P is 1, then Px is irreducible in Rx, then Px is irreducible in Rx if and only if it is irreducible over Fx. Fx means the field of fraction F. In particular, Px is monic polynomial that is irreducible in Rx. In particular, in a monic polynomial means the degree of the highest coefficient of the highest degree term is 1. That means the GCD can never be exceed 1. So if Px is monic polynomial, in particular, more precisely, in particular, if Px is monic, then it is irreducible in Rx if and only if it is irreducible in Fx. The field of fraction of R is F. Okay, so what it says that in particular for Z, Px inside the Zx and GCD of coefficient of P is 1, then Px is irreducible over Q if and only if Px is irreducible, or it is irreducible over Z. Over, oh my god, I don't know, over Z. Okay, so and similar, if it is monic, then it is also. So I am going to write a proposition here. Proposition tier 1. What is the proposition? Said that any polynomial of degree 2 or 3 over a field is always irreducible if and only if it has a root in F. A polynomial of degree 2 or 3 over a field is over a field F. Suppose over a field F is reducible if and only if it has a root in F. Okay, what is the proof of this? This is very simple proof. This is very easy, in fact. So the proof is very simple. So suppose let degree of px, degree of p is 2 or 3 and px is reducible. So px, if px is degree 2 or 3, then px will be look like some alpha x plus beta times qx or some factor, right? You can see that p of minus beta by alpha is a root, is 0. This means that p has a root in f, and here alpha and beta are coming from f, so this implies alpha by beta is also coming from f. Okay, because this is a field. What about the converse? Suppose you have degree 2 or suppose you have degree 2 or 3 and you have a root. Let degree of p equal to 2 or 3 and p of c is 0. That means there is a root for some c in the f, in your f. Then what do you think of? You have to show that this is reducible. P is reducible. So you have, since f is a field, this implies that this fx is ed, Euclidean domain. So you can use a division algorithm. Use px is non-zero and you have x minus c. So you can use this px can be written as x minus c times qx plus plus rx, where r is a remainder and degree of r is less than degree of x minus c. R equal to 0 or this happens, right? Because you have a polynomial x minus c and you have px is non-zero polynomial. So by division algorithm, px can be written as x minus c times qx plus rx, where r is 0 or degree of r, by using Euclidean algorithm or Euclidean domain algorithm. What is? So r is a constant polynomial, so r of c is 0. R is a constant polynomial and r is a constant polynomial because of this degree of r either 0 or degree of r is less than. So this is a 1 degree polynomial. So it is strictly less than, the degree of r is strictly less than this 1. That means that the r is a constant polynomial. So r is a constant poly and r of c is 0. This means that r has to be identically 0. This means that px is nothing but x minus c times qx. So this means that px is irreducible. Okay, so this is, for example, if you want to do some example. What are the example? Suppose px, you have x is cube minus 2 inside zx. X is cube minus 2 inside zx. So is it reducible? Is it reducible over z? So it is enough to show it is reducible over q. So degree of p is 3. Does it has a root? So it has a root, but this root is root x is equal to 2 to the power 1 by 3, which does not is in q. So this means that irreducible. This means that px is irreducible over q. This implies that irreducible over z. So this is not irreducible, right? These are some example. Now one proposition is called rational root test. There's one proposition, right? I'm going to write this proposition right now. So okay, one proposition. What is the proposition? Suppose px is a polynomial. Let px is a polynomial an x to the power n plus an minus 1 x to the power n minus 1 plus dot 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 plus a naught be a polynomial of degree n with coefficient with integer coefficient. Be a n degree polynomial n degree polynomial of degree n degree polynomial with integer coefficient. If r by s, you have r by s inside this Q is in lowest term, that means the GCD of r by s is and GCD of r comma s is 1. GCD of r comma s is 1, and r by s is root of, and r by s is a root of r by s is a root of px, then r divides the constant terms and s divides the leading coefficient of px. Then r divides the constant term and s divides the leading coefficient of px. That is, r divides a naught and s divides an. Are you getting what actually it says? That suppose px is a polynomial n degree polynomial with this. If the GCD of r comma s is 1 and r by s is the root of this polynomial, then r divides the constant term and s divides the leading term. Okay, r by s should be a root. If r by s, the GCD of r by r comma s is 1 and r by s is a root, then it is true, right? R by s has to be a root. Okay, so in particular px is a monic polynomial if it is px is monic with integer coefficient, and in particular px, if px is monic with integer coefficient and p of d is non-zero for all integers d, for all d inside z, dividing the constant term of px. Constant, dividing the constant term, then px has no root in q. Then px has no root in Q. So you can note one thing here. If Px is monic, then S equal to plus minus 1 and R divides A naught. So possible rationals are divisors of A naught. Possible rationals are rationals are divisors of A naught. Okay, I think it should be understood. So let me come up with some examples, otherwise it will not be clear. What are the examples? Suppose your Px is a polynomial x is cube plus 2x minus 3 over zx. What are the possible roots? Rational roots. See, R divides minus 3, constant term, and S divides the leading term 1. Okay, so what are the possible choices of R? R can be plus minus 1, plus minus 3, and S, what are the possible choice of S is plus minus 1. So what are the possible choice of R by S? R by S is 1, minus 1, plus minus 3. So P of what are R by S can be 1, plus minus 1, plus minus 3. What are the choice? These are the choice. So the possible rational roots, P of 1, you can take 1 to be 0. This is a rational root. P of minus 1, this is not equal to 0, so not a root. P of minus 3 plus minus 3 is also non-zero. So this is the possible rational root P of 1. So this is the actual called rational root criteria. So this I have written. Now I have to prove this. Whatever I have written, I want to prove this. How do you prove this? That means it says that if your this is a root, if this happens, then R by S is 0, then R divides A naught and S divides A, and this have to prove. Proof, whatever the proposition I have written, the proof of this proposition. How do you prove it? Suppose P of R by S is 0. This means that A naught plus A1 R by S plus dot 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 plus AN R by S to the power N is 0. This implies that A naught S to the power N plus A1 S to the power N minus 1 into R plus dot 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 plus AN R to the power N, this is 0. This implies that minus AN R to the power N is equal to S times, you can think of as A naught S to the power N minus 1 plus A1 S to the power N minus 2 R dot 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 plus AN minus 1 R N minus 1. So this implies that S divides AN, since the GCD of R comma S is 1. Similarly, what can you do about A naught S to the power N also can be written as R times A1 S to the power N minus 1 plus A2 S to the power N minus 2 into R plus dot 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 plus AN R to the power N minus 1, right? This implies, you can write, so this implies that this R divides A naught. says the GCD of R comma S is 1, right? So this is a simple proof. So this is called rational root criteria or nothing else. So if you want another example, I can give you one more example. What is the example? So suppose your px is x cube minus 3x minus 1 over zx. So r by x inside q, so r divides minus 1 and s divides 1 leading term and r divides the constant term. The possible rational roots what are the possible rational roots are plus minus 1. So you can check p of 1 is equal to 1 minus 3 minus 1, which is non-zero, and p of minus 1 which is equal to p of minus 1 q, this is also non-zero. So px has no rational root. This implies that px has no rational root. So this means that px is irreducible over q, because this is a 3-degree polynomial. So this is irreducible if and only it has reducible if and only it has a root. So it has no root. This implies that this is irreducible. Px is irreducible over q. This implies that px is irreducible because q is the field of fraction of z, is irreducible over z. That's it. Okay, so these are some examples of rational root criteria. You can check the reducibility and irreducibility right from here, right? Okay, what is called reduction irreducibility, that I think it is not so important. I'm not going to do this. And what else I can do is Eisenstein criteria is remaining. Okay, now I think I should have to start with the Eisenstein criteria. Eisenstein criteria I have to do. This is a proposition. I am writing this as a proposition. It's called Eisenstein criteria. Proposition. It's called Eisenstein, EISENSTEIN, Eisenstein criterion, criterion. Eisenstein criterion. What it says that let P be a prime ideal of an integral domain R. Let P be a prime ideal of an integral domain R, and let fx equals to x to the power n plus a n minus 1 x to the power n minus 1 plus dot 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 plus a naught be a polynomial in Rx. Suppose a n minus 1, the coefficient a n minus 1 dot 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 a1 up to a1 a naught are all elements of P, of this prime ideal P, and suppose a naught is not an element of n. Suppose a naught is not an element of is not an element of P square, then fx is irreducible in Rx. Irreducible in Rx. Okay, so this essentially means that this a n minus 1 is 1 should not be in a n minus 1 up to a naught is all all are a member of this prime ideal P, but a naught should not be a member of P square, then fx is irreducible. And this is in general Eisenstein criteria, and there is a simpler version of z over zx and qx. Over for zx and qx is a simpler version what it says that suppose px p of x equal to a naught plus a1 x की power 1 plus dot plus a of n x की power n over qx or zx, whatever, it doesn't really matter. So, and p be a prime number, let p be a prime number, p be a prime number is that p divides a naught, p divides a1, p divides a n minus 1, but and p square does not divide a naught, then p is irreducible over px is irreducible over zx or qx, whatever. Okay, I think this is understood. So your p should divide a naught, p should divide a1, p should divide up to a n minus 1, but p square should not divide a naught. Then I will say that this px, what px means the polynomial, whatever the polynomial is, px is irreducible over zx or qx, whatever the. Okay, so look to think about examples. So x to the power n minus p is always irreducible over q or z, doesn't really matter, by Eisenstein. Each means Eisenstein criteria, because see, p divides c, what is this, our a naught term is p square, p divides p square does not divide p, so this implies that this is irreducible. First example. Second example, what it says, second example you can choose to be x to the power 4 minus plus 10x plus 5 over zx. Five divides 5 divides 10, but 5 square doesn't divide 5, so irreducible. Right? So these are some examples. These are some very simple examples of Eisenstein criteria. Again, very easily you can check the criteria. Now I am going to write one proposition, this involving Chinese remainder theorem. This is an important proposition for the exam perspective. Exam means the competitive exams, the entrance examinations. I am definitely not going to prove this proposition, so I am writing this proposition, okay, and I will make you understand what is actually happening. Let gx be a non-constant element of fx. Suppose let f be a field, and gx be a non-constant element of this fx. and gx, and the gx, it should be variable, should be there, gx, suppose f1 of x to the power x1, sorry, n1 means the power n1, f2 of x to the power n2, fk of x to the power nk. Be its the factorization into irreducible, be its factorization into irreducible, factorization into irreducible, where fi's are distinct. fi's are distinct. Then we have the following isomorphism of rings. Then we have the following isomorphism of rings. What is the isomorphism? Then fx by ideal generated by gx is isomorphic to fx by ideal generated by f1 of x to the power n1 cross fx by ideal generated by f2x to the power n2 cross dot 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 plus cross f of x by ideal generated by fk of x to the power nk. Right. So this has the following isomorphism of rings. Okay. So based on this, I am doing this question, one question. One question I should have, yeah. Based on this, you just solve this question. What is that? Yeah, this is okay, right? Yeah. So suppose your ring R, is Cx by ideal generated by x square plus 1. Then suppose this is here to be R, say. Then choose the following: the dimension of R over C as a C vector space. Dimension of R over as a C vector space. As a C vector space is 3. 2 says that R has 2 prime ideal. R has 2 prime ideal. Has exactly 2 prime ideals. Third says that R is a UFD. R means the entire structure. And the fourth one says that ideal generated by X is maximal ideal in R. Is maximal in R. Which of the following is or are true? So try to use this. Use the previous one. Whatever the result I have written, and try to solve this question. As a C dimension of R, the dimension of R as a C vector space is 3. R has exactly 2 prime ideal. R is a UFD and ideal generated by R is a maximal ideal. Choose the correct ones. Let me check something. Started with okay. Have you so which one of them are true or which one of them are false? So you just have to see the you can definitely talk about the last whatever I have written lastly what I have told you. See your gx is an irreducible factor. These are the irreducible factors of gx. Then your fx by ideal generated by gx can be isomorphic to this. So your x square plus 1 can be written as x minus I x plus I over c, right? So you can use this cx by ideal generated by x minus I or x square plus 1 x square plus 1 is isomorphic to cx by ideal generated by x square x minus I cx by x plus I is I, right? So this what are these structures? This is isomorphic to this and this is isomorphic to this is C and cross C, because you just have to define a map P of I goes to I, P of x goes to P of I and P of x goes to P of minus I, right? So this is C cross C because this is isomorphic to C and this is isomorphic to C. Okay, this is C cross C. So C cross C, what are the ideals of C? Because ideals of C cross C are ideals of C and the zero ideals are 0 cross C and C cross 0, C cross 0. This is maximal and no other will be a maximal ideal because C plus C. So it has exactly two proper ideal. This option is correct. These are exactly two proper ideals. So what is it a three-dimensional space as a C vector space? Is it a three-dimensional space? So okay, what do you think? Okay, yeah, this also helps help you to solve that. This is also false. C cross C is a how many dimension? This is actually isomorphic to C cross C. The C dimension is a two-dimensional space. So you can think about this is also false. This is C cross C. So C cross C is not the dimension. C dimension of C cross C is not 3. This is a two-dimensional space. Okay, so What do you think of others? That the ideal generated by x is maximal ideal. What do you think? It is ideal generated by x is maximal or not? What do you think? Okay, and the first question is, and the other thing is, R is a UFD. No, R is not a UFD. Because you see that C cross C, this is C cross C, and C cross C is not an integral, you can take to be 1 0 0 1. This is 0, so this is not an integral domain, so it can never be UFD. So now this is your exercise to think about whether R is maximal or not. Okay, so this much. Similar question for if you same question I ask you for, if I ask the same question for qx by ideal generated by x square raised to the power 4 minus 1, what do you think of over qx or zx? Okay, so x to the power 4 minus 1 can be x square plus 1, x square minus 1, right? So it further can be written as x plus 1, x minus 1 into x square plus 1, right? So this is irreducible, this is irreducible, this is irreducible, this is irreducible. Now your qx by ideal generated by x to the power 4 plus 1, sorry, x to the power 4 minus 1 is isomorphic to qx by ideal generated by x plus 1 into qx ideal generated by x minus 1 into qx ideal generated by x square plus 1, right? This is isomorphic to q, this is isomorphic to q, and this is isomorphic to qi, right? So the same question and same kind of argument you can definitely talk about. Now I am going to say about talk about some which is called the application of Eisenstein's criteria. It is called cyclotomic polynomials, and the cyclotomic polynomials are always irreducible. Okay, so the irreducible factors of x to the power m minus 1, which are precisely called the cyclotomic polynomials, MS cyclotomic polynomials. So for that, the irreducible factors of x to the power m minus 1, x to the power m minus 1 are actually product of summation d divides m phi of d of x. Suppose if you have x minus 1, this can be written as x minus 1, there is no other choice. This is actually named it as phi 1 of x. This is called first cyclotomic polynomials. You can take it the x square minus 1. This can be written as x minus 1 into x plus 1. This is actually phi 1 of x, phi 2 of x. X is cube minus 1. This can be written as x minus 1 into x1 x square plus x plus 1. This is actually phi 1 of x, phi 3 of x, phi 3 of x, right? So similarly, x to the power 4 minus 1, this is actually x minus 1, x plus 1, x square plus 1. This is actually phi 1, phi 2, 5 4. So this is actually written in this format. This is called mth cyclotomic polynomials. If somebody, and the cyclotomic polynomials are always irreducible. I will show you. I will very soon I am going to show you. Cyclotomic polynomials are always irreducible by Eisenstein's criteria. I will. Okay. So similarly, if you want x to the power 5 minus 1, this can be written as x minus 1 into 1 plus x square plus x cube plus x to the power 4 is equal to 5 1 5 5, right? 5 cyclotomic polynomials. So if you want to know about the cyclotomic polynomial, then you have to put some group theoretic concept. Okay. And the degree of, and you can say the degree of phi m of x is equal to Euler's torsion function phi x, phi of m, and degree see here the x is cube 3D. This is a 3 degree polynomial. Okay, phi 1 into phi 5. The degree of 5 is 4 degree polynomial. Degree of 4 is 2 degree polynomial. So these are some basic examples, and I am going to write a note over here, right? So one note, and the application, you can say you can use the irreducibility of Eisenstein's criteria. So if f is a field, and px inside fx is irreducible, over f, if and only p of x plus a is irreducible over f for every a inside this f, for any. Okay, so now I am going to application of this. Application, how do you apply this? Suppose px you have given to be 1 plus x square plus you just first I can work with some x to the power 4, suppose x to the cube plus x to the power 4, okay, over z. So this can be written as x to the power 5 minus 1 by x minus 1. This is irreducible, this irreducible, sorry, px is this. So px is irreducible if and only p of x plus 1 is irreducible, right? So what is p of x plus 1? Is equal to 1 plus x to the power 5 minus 1 divided by 1 plus x minus 1. This is actually equal to 1 plus x to the power 5 minus 1 divided by x. This implies that, but binomial expansion you can think about 1 plus 5 choose 1, I guess, right? 5 choose 1 x plus 5 choose 2 x square plus plus x to the power 5 minus 1, right? Divide by x, you just divide by x, and 1 on 1 will be cancelled, and it will be something like 5 choose 1 plus 5 choose 2 x plus plus 5 choose 4 x is x to the power q plus x to the power 4, right? So but 5 divides a naught, 5 divides a1, 5 divides a2. See, this is your a naught, this is your a1, this is your a2, this is your a3, this is your a4. 5 divides a3, but 5 doesn't divide, 5 square doesn't divide a naught. This implies that by adjacent p of x plus 1 is irreducible. This implies that p of x plus 1 is irreducible. Oh my god, my battery is low. Just a second, just give me a moment. I don't know. Okay, so by Eisenstein's criteria, so p of x plus 1 is irreducible. This implies that p of x is irreducible by Eisenstein. Okay. So in particular, if p is any prime, in particular, if p is prime, then 1 plus x square plus dot 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 plus x to the power p minus 1 is always irreducible over z or q, because if it is irreducible over z, it has to be, if it is irreducible over q, it has to be irreducible over z, right? So this much you have to, just a second, yeah. So this is irreducible over q. Okay. So similarly, the cyclotomic polynomials what I have written, they are always irreducible, because if somebody asks you to compute the phi 12, okay, suppose if somebody asks you to solve what is phi 12 of x, that means the phi 12 means the 12th cyclotomic polynomial. Degree is a 4 degree polynomial, it will be, because phi 12 is 4, the Euler torsion function or Euler's phi function is 12. So suppose somebody asks you to solve phi of 12 of x, find what is the degree of phi 12 of x. This polynomial has degree phi 12, that means 4, torsion function, Euler's. So x to the power 12 minus 1 can be written as, see, it can be written as a product d divides 12 phi d, right? So this can be written as phi 1 divides 12, phi 2 divides 12, phi 3 divides 12, phi 4 divides 12, phi 5 no, phi 6 definitely, and phi 12 divides 12. And this is, it can so this x to the power 12 minus 1 also can be written as x to the power 6 minus 1, x to the power 6 plus 1, right? And x to the power 6 minus 1, x to the power 6 minus 1, okay, x to the power 6 minus 1, x to the power 6 minus 1, so phi 1, acha, yeah, x to the power 6 minus 1 will be cancel out to 1 2 3 6 up to, okay, cancel out, and we will left out with x to the power 6 plus 1 equal to 1 2 3 5, okay, 4 is here, phi 4 phi 12. This is actually x to the power 6 plus 1 can be written x square cube plus 1 cube equal to 5 4 512. This is actually equal to x to the power x square plus 1 x to the power 4 minus x square plus 1 is equals to 5 4 512. But this will cancel out with 5 4 because this is 5 4. Okay, so this implies that your 512 of x, this is actually x to the power 4 minus x square plus 1, and this is irreducible. Okay, so this is a 4-degree polynomial. This I think this much. Up to this is okay over ring theory, I guess. So I will take one more lecture, I guess, to define Noetherian ring and Hilbert-Bess's theorem over commutative ring. So let me check once whether I have completed everything or not. So is there anything missing I have missed or not? I don't know. Okay, 5p is, I'm saying 5p is irreducible. Okay, 5 for 512 is not irreducible, I cannot guarantee, but 5p is always irreducible. Okay, no, 5d is also irreducible. 5p is okay, 5m is always irreducible. Okay, but how do we show the irreducibility of this? Each 5Ds are actually irreducible. Let me check whether I have missed anything or not. Okay, it seems that I have completed everything. One or two things remaining. Okay, so then the next session I will discuss about some problem session. Okay, I think everything has to be, so try to solve the questions from at least from dummy today, and if you want more problem, then you can solve research long algebra from ring theory part. I guess I have completed everything. Let me check just 1 second. One more lecture is remaining. Here I will define what is Noetherian ring and Hilbert-Bess's theorem. That will finish our course in ring theory. One more lecture will be, at most one lecture will be there. I have not completed everything, but more or less the everything what about the up to undergraduate level, up to entrance level, I have completed, because this much is enough, more than sufficient. The only one thing is remaining is the solving question. We have not solved enough question yet. We have to solve too many questions. I have to collect it, and I have to collect it, and I will solve most of the cases. Particularly I will solve the previous year questions from the entrance examinations. Okay, I will solve them. I think I have completed everything, so nothing is remaining up to the solve. Just let me show you. I guess fundamental, no. We'll solve these questions. Yeah, polynomial ring I have defined today. So this much, this Eisenstein's criteria. Polynomial ring over a field, this I have defined, this I have discussed. This much we have discussed. Polynomial unique factorization domain. Okay, that we have discussed. Reducibility criteria we have discussed. All the things we have discussed, I guess. Here is the cyclotomic polynomial. Consider the polynomial this cyclotomic polynomial. See, there is this exactly same thing lastly I have defined. After that, nothing is remaining, I guess. Polynomial ring over fields. Yeah, this also we have discussed. This, right? Chinese remainder. Okay, the proof will follow from the Chinese remainder theorem, but okay, polynomial over several variable over the Grosvenor basis. Don't worry about the Grosvenor basis. Yeah, I'll state Noetherian ring. In the next lecture, we'll define what is Noetherian ring and Hilbert basis theorem. After that, we'll come to Grosvenor basis. Don't worry about the Grosvenor basis. General polynomial division. No, this is not needed for you. Whatever we have discussed, this is more than sufficient according to the syllabus of the book of this Jamid and Poti. Grosvenor basis is completely of commutative algebra, so this is not a part of ring. Is a basic ring theory course. This is a part of commutative algebra. So I think we have defined everything. We have completed everything. Now we are just only left out. Okay, modules and next we'll define about modules. So this much is for today, I guess, and the next lecture within today, I think I will today within today or tomorrow I will finish the whatever the remaining one is. Might be the problem solving session will be 1 or 2 lectures, and one lecture is from Noetherian ring and Hilbert basis theorems. Up to that I can say. So this is enough, I guess, for today, right? So thank you for watching, and more or less you can assume that we have completed all the syllabus of this ring theory course. There is nothing is remaining. The theory part is completely over. One thing is remaining, but this is not needed. I think this is for extraordinary. So Noetherian rings and Noetherian Artinian ring. I will define everything. I will define, but more or less the ring theory part is going to finish. And now whatever we'll do, we'll do some commutative algebra things. That is a part of commutative algebra, not in ring, but that will help you much in this ring theory course. So this is the part of commutative. Whatever I am defining in the next lecture, this is a fully a part of commutative algebra, right? So now don't worry about this. Now your ring theory course is finished. So that is for today. So should I have can I give you one question? So I can give you one question, right? For solving, I will solve in the next lecture. Okay. So you know that set of all continuous functions from C01, right? What is, C01? Set of all f from 01 to R. F is continuous. So what are the ideals of C01? What are the ideals of C01? What are the maximal ideals? This is a ring. First of all, you show that this, so that C01 is a ring with respect to the as usual addition and multiplication. It is a ring. First of all, you show that this is a ring. What are the ideals of this C01? What are the maximal ideals of this is a very good question. Okay, this oftenly I asked in interview, in most of the interviews, which whoever said in interest is ring theory on suppose algebra, then you have to, this is a very good, very nice question. What are the maximal ideals of C01? And show that every maximal ideal of C01, first is this, second is this, and the third is show that every maximal ideal, show that the every maximal ideal of C01 is of the form suppose J or I all those f inside C01 such that f of C is 0 for some C inside this R over real valued. Okay, I am going to real values, so for some C inside R. This is the maximal ideal, and every maximal ideal are of this form. You have to show in this three question I am expecting you to do. Okay, and this is a very nice question. At least once in your life solve this question, and it will never be you will never forget this. Okay, and I will solve this in the question session, not in the next lecture, because next lecture I am going to do some theory, okay, of commutative rings. It is called commutative algebras. So this question you can solve, and the rest of the questions, the previous year question, I will solve in the problem session. Okay, so now I think I'm done for today. I think it's been 2 hours and 2.5 hours has already been. Okay, so goodbye everyone. So this is the end of the course of this ring theory. Thank you.